you should have access to the PDF file that contains all the acronyms for the session. And not only that, we have a separate PDF file that has acronyms for the entire series. So feel free to have those handy. And of course, I'm here for you. Anytime you want to find the full name, just send your question my way. Okay? Okay. Okay. Now, this is what we plan to accomplish today. We would take a look at the structure of the air interface. So we'll see that we have slot, subframe, and frame. These are the timing structures that we'll take care of. We would be able to tell the difference between the resource elements and so-called resource blocks. How is a virtual resource block related to a physical resource block? We'll take a look at that. There are various channels and signals defined for the downlink, also for the uplink. So we'll take a look at various channels and the signals, basically how we use those channels. That would be the main focus. So this is what we will cover today. Okay. And if you do not have any comment, please feel free to change the color of your seat to green. Okay. If you have any color other than green, then we will know that, oh, you have some feedback for us. Okay. Okay. Let's say I have 10 megahertz bandwidth. Within that 10 megahertz channel bandwidth, we would transmit our subcarrier in specific portions. Okay. So let's say the maximum portion that we will use for actual subcarrier transmission would be so-called transmission bandwidth. And that transmission bandwidth is quantified in terms of number of resource blocks. Now, what is one resource block? A resource block has a dozen consecutive subcarriers. Okay. So if I have one resource block here, inside that we have 12 subcarriers and so on. So if I have 10 megahertz bandwidth, then inside the 10 megahertz bandwidth I would have 50 resource blocks. Okay. And it is scalable. So if you have 20 megahertz, you have twice as many resource blocks. So 20 megahertz would then have 100 resource blocks. Okay. So the number of resource blocks is scalable. That's why we said, oh, we are using scalable OFDMA in the downlink, scalable SC-FDMA in the uplink. Okay. So as you can see from here, we have some portion inside our 10 megahertz bandwidth that we are not using to transmit any subcarrier. So you can think of such portion as guard. Okay. So that is your guard band, so that we minimize interference caused to the left and right side of the spectrum. Maybe some other operator is on the right hand side. Right? Maybe some other operator is on the left hand side of the spectrum, and so we want to minimize interference, and that's why we have these guards. Okay. Okay. Here are the basic characteristics of the air interface. So we have covered in the last session that the downlink utilizes orthogonal frequency division multiplexes, and the uplink we use a variation of that called SC-FDMA, single carrier frequency division multiplexes. Okay. Now, the sessions are independent from one another. So if you do not know the answer to a question, don't worry. We will make sure that we provide the adequate information. Okay, so that the sessions remain independent. In case you have attended a session in the past, you can answer the question, why are we using HCFDMA in the uplink? You can give me the answer by typing in through questions box. So the main reason for that is we want to reduce something. What are we able to reduce? We are able to reduce something. Okay, looks like we have some answers coming in. Okay, perfect. Peak to average power ratio. Okay, very good. Thank you for your answer. So the reason that we have this SCFTM interlink is to reduce peak to average power ratio. Okay. And basically, you can translate that into one of the two things. Either we are able to increase the cell size, or we are able to improve the cell edge performance. So one of the things we are able to do, okay, by reducing the peak to average power ratio. Okay. And in terms of duplexing, we support time division duplexing, frequency division, and half FDD. Two radio frame structures have been defined, type 1 and type 2. Type 1 is for FDD, and that is our focus. So we will not talk much about the type 2 structure. Okay. Someone has a question on difference between TD and FTD. Okay. Now, I will give you a short answer. So basically, FTD means that from base station to the device, we have one bandwidth reserved, 10 megahertz bandwidth, and also from user to the base station, we have another part of the spectrum reserved. So we are using 20 megahertz total bandwidth, and we are able to do transmission and reception at the same time. Exactly at the same time, the mobile receives information, mobile transmits information. In case of time division duplexing, we just reserve one part of the spectrum for both downlink and uplink transmission. So sometimes we will use that spectrum bandwidth for transmission, sometimes we will use the same bandwidth for reception. So either transmit or receive only one of the two at a given time instant, that is TDD. Okay, but if you want more, then we can discuss later. Okay. So hopefully this is adequate. Okay, so we will be focusing on type 1. Okay, type 1. Okay. Scalable OFDMA system. So as little as 1.4 megahertz bandwidth is good enough to deploy LTE, and the largest bandwidth available in LTE is 20 megahertz. Having said that, the most likely deployment would be 10 megahertz. So we believe that 10 megahertz uplink and 10 megahertz downlink, total 20 megahertz spectrum. That's what you would see as the most common deployment configuration for LTE, at least initially. Now, after you type in question, I will send a quick acknowledgement. Okay, or okay, something like that I will type in. And when, at a certain time, I will provide answer to your question. Numerous advanced antenna techniques are available for use. So for example, MIMO, multiple input, multiple output, is one example of such technique. So quite flexible. You can deploy LTE wherever you have spectrum. So 700 megahertz, maybe 2 gigahertz, right? Wherever we find spectrum, we can deploy LTE. So we do not have too many constraints on that. In fact, if you find spectrum somewhere, then LTE standard will say, okay, no problem, we will accommodate you, because we want as wide acceptance of LTE as possible. So quite flexible. In the US, 700 megahertz would be quite common. Both AT&T and Verizon Wireless have 700 megahertz spectrum. So again, we believe that 700 megahertz would be the initial deployment carrier frequency. So those are the main features of their interface at a high level. Okay. Okay. If using FTD, the question is, do we have to have separation? Yes. And that separation primarily comes from the regulation that a specific country has. Okay. So, for example, the cellular band, we will have certain separation for the PCS band, for 700 megahertz, for AWS spectrum. There will be specific separation. But in the US, for example, the Federal Communications Commission will control that because we'll have a licensed spectrum with specific portion up for uplink, specific portion for downlink. So in theory, it can be contiguous, but in practice, since we have to rely upon the government authorities and we want to make sure that we do not have interference between those bands, we normally have separation. Okay, so we normally have separation. And typically that is dictated by the interference between the two and the government regulations. Thank you for your question. And of course, anytime the answer is inadequate, you want more details, you want better explanation, just ask a follow-up question or use the audio bridge whenever we unmute. Okay? And again, we welcome your questions. As I mentioned, we'll be focusing on FDD, frequency division duplexing. That's why we are showing you here type 1 frame structure. We have 10 millisecond radio frame, and within that 10 millisecond radio frame, we have 10 subframes. So subframe 0 all the way up to subframe number 9. Those are the subframes that we have. 10 subframes in one 10 millisecond frame. So that will make our subframe 1 millisecond long. And within a subframe, we have 2 slots. Time slot 1, time slot 2. 2 slots within a subframe. So that will make our slot half millisecond long. Now, why do we have all these kinds of timing structures? So we have given here some basic idea behind that. So the reason that we have frames is the information about the system is sent in the units of frame. So for system information, we do that. Why do we have subframe? The subframe is primarily for resource allocation. So for example, in the early part of the subframe, the base station will convey to this UE that I am giving you 10 resource blocks. Okay. So that kind of information is contained inside the early part of the subframe. Maybe in the next subframe, I will tell the user, okay, I am giving you all the 50 resource blocks that exist within the 10 megahertz spectrum. So we are giving the whole bandwidth to a single user. So as you can see, from one subframe to the next, we can change things around. We can change the data rate, change modulation, change coding, etc. Okay. So that is the idea, that we can dynamically adapt the resources to the existing channel conditions very, very fast. Very, very fast. And just for your information, in 1XE video, we have 1.67 millisecond slot, right, in 1XE video. So you can change things around every 1.67 millisecond if you keep DRC length 1. And here we change things every 1 millisecond, both in the downlink and the uplink. In the reverse link or uplink in DO, the fastest you can change things around is every 6.67 milliseconds. That is in the reverse step. So we are doing things now much faster in LTE. Every millisecond we can change uplink situation, change downlink situation. Okay, so resource allocation is done per subframe, and subframe also helps us with frequency hopping. Why do we have slots? The slots will help us with synchronization. So once the power of the UE is turned on, it will use the help of the slots to synchronize in terms of the time and frequency with the network. So for synchronization, very, very useful. Also, frequency hopping can be implemented for slot. So those are the main things regarding the timing structure. We have a question. Do FDD and half FDD mean the same thing? Do they mean the same thing? Not 100%, but almost. So for example, FDD, we can have simultaneous transmission and reception. So we transmit on, let's say, F1 carrier frequency, receive on another carrier frequency F2 exactly at the same time. However, in half FDD, in the half FDD, we can do either transmission or reception, not both, either transmission or reception. When we do the transmission, we will use one frequency. When we do reception, we will use another carrier frequency. So even though our mobile device can operate on two different frequency spectrum, it can do those only one at a time. So either it will use carrier frequency F1 for transmission, or it will use carrier frequency F2 for reception, but only one at a time. In full FDD, you do both transmission and reception exactly at the same time on two separate carrier frequencies. I am not aware of any operator thinking of deploying half FDD terminal. From the base station's perspective, base station is always operating in the full FDD mode. Okay, so base station transmits on one carrier frequency, receives on one carrier frequency all the time. From the mobile device's perspective, from that perspective only, it will transmit on one carrier frequency or it will receive another carrier frequency at any given time. So again, I believe that full FDD would be the basic deployment. Okay, no information on who is interested in half FDD, but it is there. So if you want to have low cost devices, then they could also deploy, utilize LTE, but I'm not aware of any operator yet. Okay. And in the same spectrum, yes, two UEs can coexist. Yes. So for half FDD UEs, the base station scheduler will make sure that it will not schedule the user at a time where the user is not supposed to do transmission or reception. Yes, so we can share the same spectrum between two types of UEs, half and full FDD. Again, thank you for your question. Keep your questions coming. Okay. Let's see if any other. Okay, one other question. Oh yes, the timing structure that we have defined here, it is applicable to both forward and reverse. Yes. So we can do that. Absolutely correct. So this structure is valid for both the directions. Frame, subframe, time slot. Those three timing structures are available for both the directions. Forward link, reverse link, down link, and up link. Okay. Okay, looks like we have covered all the questions. Okay. Very good. Only you know what you would like to ask. What is in your mind? So please send me your question. Okay. We want to make sure that everyone gets answers to that question. Okay. Very important concept here. Resource element and resource block. Now, here is one resource block. we already know how many subcarriers. We have a dozen subcarriers within a resource block. Now, from the timing perspective, how long does a block last? So, basically, the block will last for one slot. So, in this example, I have this half millisecond slot. And inside that half millisecond slot, I have 7 OFDM symbols. 7. 0 through 6. Total of 7 symbols. Do you remember the approximate length of the OFDM symbol? How many microseconds? How many microseconds for this symbol time? OFDM symbol time. Approximately how many microseconds? And okay, looks like a lot of people are paying attention and answering questions. Very good. Thank you for your answer. Yes, so 66 microsecond is the useful symbol time or modulation symbol period. And add to that cyclic prefix, let's say about 5 microseconds. So total 71. So this more accurate number is 4.69 short cyclic prefix. So if you are using short cyclic prefix or cyclic extension, then the total symbol time is 71. Okay, and if you multiply 71 by 7 symbols total, then you will get 497 microseconds, which is close to 0.5 milliseconds. Okay. So if you do the exact calculation, it will be exactly half millisecond. We are doing some small approximation. Okay. But basically, a half millisecond slot would contain 7 symbols if we are using short cyclic prefix. So in summary, our one resource block contains a dozen subcarriers here and one slot. And inside the slot, we may have 7 OFDM symbols. So we understand now resource blocks, basically a dozen subcarriers that will last for 1 half millisecond slot. Now, where is this resource element? Very simple. A resource element is nothing but one subcarrier for the duration of one symbol. So this is one resource element. This is another resource element. Another resource element. So one subcarrier and one OFDM symbol. That would be your one resource element. So if I have one resource block that has 12 subcarriers and it has 7 symbols, 12 subcarriers and 7 symbols. So together I would have 12 multiplied by 7, 84 resource elements. Okay. Yeah. Now this live meeting is quite nice. That helps us have this session. But the resolution is not as good as we would like to have. So hopefully you can still read my handwriting. Okay? I will try not to write too much. I will try to write slowly. So hopefully you can see this. Okay? But thank you for your cooperation in this regard. So we have one resource block having 84 resource elements. So that's the definition. Okay. Okay. Having said that, now the question is, how do we allocate the resources? What is the minimum allocation? The minimum allocation is 2 resource blocks in a subframe. That is the minimum allocation. So if you are a UE and if you are allocated something by the E node B, then E node B will give you at the minimum 2 resource blocks. One resource block in one slot, another resource block in another slot. So 2 resource blocks total in the subframe, that would be your minimum allocation. So the resource allocation is done in the units of these resource blocks. Okay, so that is the idea. 2 resource blocks is the minimum allocation. Now there is something called physical resource block and virtual resource block. Okay, so virtual resource block VRB and physical resource block PRB. So let's say I have a 20 megahertz spectrum. Inside the 20 megahertz spectrum, I would have 100 physical resource blocks. And we already know that one resource block has a dozen subcarriers. So we will have basically a total of 1200 subcarriers. So the physical blocks, they are just neighbors of one another. So physical block 0 is next to the physical block 1. Physical block 1 is next to the physical block 2, and so on. So those are basically the contiguous resource blocks. Okay, physical resource block. Now, where is this virtual resource block? Well, the standard says that I have this virtual resource block, I have these physical resource blocks, and when I want to convey certain type of allocation to the user, one way to do that is to specify virtual resource block. Okay. So there are many ways of allocating resources, and one of those ways is to convey the allocation in the terms of virtual resources. Okay. So I would tell the user that, okay, I am giving you virtual block number maybe 11, 12, and 13, let's say. So we are conveying the allocation in the VRB form. We are not conveying the physical resource block, we are conveying the virtual resource block. And then the UE will use a formula for frequency hopping, and that formula has some other inputs also. For example, identity of the cell, then identity of the subframe, what is the number of the subframe, etc. But basically, we have some formula defined in the standard, and one of the inputs is the virtual resource block. So that virtual resource block will correspond to specific physical resource block. So maybe, let's say I have virtual block number 11. That may correspond to physical block number 2. Okay, that is the idea, that we will have a mapping between virtual and physical resource block. Now let's take an example. Let's say that we do not want to do any kind of frequency hopping. So whatever virtual block number we have, that would be the same as the physical block number. Okay. So in one slot, okay, virtual block number is the same as the physical block. Let's say we have another slot, right? Maybe the next one in sequence, again, no change. So if you do not want to do frequency hopping, then the virtual and the physical block numbers, they are the same. So basically, we are just essentially specifying physical resource block. So there is no frequency hopping in that case. Now what happens when you do have frequency hopping? So let's say that our base station has given the block number X to the UE. That, hey UE, I am giving you virtual block number X. Then we will give that number to this formula, and it will give us the physical block number. So it may correspond to, let's say virtual block number 10, may correspond to physical block number 10 in one slot, and in the next slot, maybe it will correspond to physical block number 20. So the same virtual block number corresponds to different physical block numbers in different slots, because one of the inputs into the frequency hopping algorithm would be slot number. So this is just one example. And if you are interested in more details, you can look at the standard and you will get a quite well outlined mechanism of calculating the physical block number based on some virtual block number. So let's summarize. Virtual block number and physical block. There will be some relationship, and that is defined by the standard. And the relationship depends on whether we are doing frequency hopping or not. And one way to allocate resources is to indicate to the UE virtual block number, and then it will be mapped onto specific physical block number based on the standard defined approach. But regardless of virtual block or physical block, it doesn't matter whether we are talking about virtual block or physical. Within that block, you will always see consecutive subcarriers. So within one virtual resource block, a dozen consecutive subcarriers. Within one physical resource block, a dozen consecutive subcarriers. Okay, so the folks who are familiar with WiMAX is different. WiMAX, you could have distributed subcarriers allocated to the user, but here in LTE, we have within a block consecutive subcarriers. Okay, so that's one of the differences between LTE and WiMAX. Here we have always a dozen consecutive subcarriers within a virtual or physical resource block. We have defined a concept called resource element groups, primarily to help us send out control channels from the base station. So here is our E node B, and E node B wants to convey allocation of resources to the user, right? And I mentioned that we can give one or more resource blocks, and we can do that by specifying those in the early part of the subframe. If I have a 1 millisecond subframe, the early portion of that here will contain resource allocation. Okay. There will be some sort of channel, control channel, that would indicate the resources for a given UE. So basically, we want to convey allocated resource blocks to a UE. And to help us do that, we have defined these resource element groups. So let's take one example. Let's pick this resource element group. So that is one resource element group. Inside that resource element group, we have, in this example, a total of 6 subcarriers. 6. So 0 to 5. Right? A total of 6 subcarriers. Within the 6 subcarriers, we will not use the subcarrier number 0 and subcarrier number 3 for the control channel, because those are our so-called reference signals. It's like pilot. Pilot is your reference signal. So it means that we have basically to exclude those from our list of subcarriers that can carry our control channel. So we are left with then 1, 2, 3, and 4. So even though my resource element group contains 6 subcarriers, 2 are actually reserved for our reference signal. So we cannot use those. So essentially we are left with 4 subcarriers, and those are the subcarriers that will help us carry 4 modulation symbols. So if you recall, one subcarrier carries 1 modulation symbol during the symbol time. So our resource element group will be able to carry 4 modulation symbols because we have 4 subcarriers. That is the idea. So basically, one resource element group will always help us send out 4 modulation symbols. So let's take another example. Let's look at this. Okay. So we have basically now this resource element group that has 4 consecutive subcarriers, 1, 2, 3, and 4. So we will create one resource element group using that set of subcarriers, and 4 subcarriers will help you carry 4 modulation symbols during the OFDM symbol time of about 71 microseconds when you are using short cyclic. So in summary, the reason that we have so-called resource element groups is to be able to send out control channel. So our control channel will occupy several resource element groups. But this kind of structure helps us put together the contents of the control channel. And that control channel will convey uplink resources to the UV, downlink resources to the UV. Okay, looks like I talked for quite a while. So time for me to ask you a question. And once you are done with this, we will answer your question regarding frequency hopping. So I will give you a couple of minutes to work on this, okay?
Nishis, are you there?
Oh, yes.
All right. I just did not hear you. Want to make sure.
Oh, no, I was not speaking.
Okay, very good.
Saving my energy to shout later.
All right.
Please participate in the poll. So far we have 19 folks who have provided answers. The rest of them, about 7, 8, they are on a vacation. So please come back from your vacation. Or maybe you are thinking. Good to think. So please think and then click. I will give you maybe 1 more minute. $30 seconds. And we are looking for a false statement, not the correct one, not the true one, the false statement. So out of 3, 2 are correct. Okay, so let's share the results. Oh, now the second option is the incorrect statement. As I mentioned earlier, it doesn't matter whether we have physical resource block or a virtual resource block. Within a block, we will always have a dozen consecutive subcarriers. So the LTE system does not give you an option that, oh, go ahead, you can have distributed subcarriers. No, not possible. Within a block, always consecutive subcarriers, neighbors of one another. Okay, so that is not correct. Option number one, of course, that is true. You can change things around every millisecond because at the beginning of every subframe, you can give different numbers of resource blocks to the user. So sometimes you can give one resource block, the next subframe, you can give the user all the resource blocks. So we are able to change the data rate every millisecond, every subframe. And the last one, virtual resource block. So I showed you a formula, simple mechanism that the same virtual block corresponds to potentially different physical blocks in different slots. So that is one way of implementing frequency hopping. Okay. Frequency hopping means that the information about the user is sent over different subcarriers. Okay. Someone has a comment that the green and the orange resource blocks do not seem to be in the fixed place. Okay, let's actually we were for the frequency hopping, we were thinking like this, that if I want to implement if I want to implement frequency hopping, then I will give some virtual block number, let's say X. It will correspond to one physical block in one slot, and the same number corresponds to another physical block in another slot. So our user will get data, let's say during slot 0, it may get data on physical block number 20, and in the next slot number 1, right, it would get data on another physical block, maybe physical block number 30, depending on this frequency hopping formula. So hopefully that is clear, but we can discuss later, okay, when we unmute the bridge. So if you want to have additional discussion, we'll do that, okay, when we unmute the bridge. Not yet, after some time. Okay, now we have one outstanding question. What is the purpose for having frequency hopping? To exploit frequency diversity, not for security. We do frequency hopping for security in frequency hopping spirit spectrum. In military, we use that, but we are not fighting anything here. We are just trying to implement frequency diversity. So maybe sometimes one part of the spectrum is experiencing a fade. So at that time, another part of the spectrum is probably experiencing good channel conditions. So if you keep hopping, then you are not likely to be stuck in the same poor channel conditions for a long time. So in summary, the reason for having frequency hopping here is to exploit frequency diversity. Very good question. Very good question. Okay. Okay. So hopefully things are now a little clear. Okay. So most of you, it seems, have 1x and 1x video type background. Some of you probably are familiar with a little bit of UMTS, but most of you have 1X background and DO background. So this will be a little bit new to the 1X and DO folks. In basic UMTS, we have defined 3 types of channels. Okay. We have logical, transport, and physical. 3 types of channels. Why do we have 3 types of channels? Well, UMTS. It has to be complex. Okay, cannot be simple. That's one answer. But let's see what those channels are for. Logical channel. It indicates what kind of information are we sending. Are we sending some broadcast information? Are we sending some dedicated traffic for a user? Maybe some sort of email. So broadcast will be on broadcast control channel. That's one logical channel. User traffic such as email, that would be on another logical channel. Dedicated traffic channel. So logical channel basically tells us what are we sending, what kind of information. Then we have transport channel. And transport channel tells us how we are sending the information, how we are protecting the information. For example, if it's voice, surface switched voice, then we traditionally rely upon convolutional coding. So that will be on one dedicated channel 1. That would be a transport channel. For our packet data, where we may have thousands and thousands of bits, and then we need a very powerful coding mechanism, and turbo coding will help us protect the information. So we are doing a different type of protection, different type of redundancy. So that would be another transport channel, dedicated channel number 2. So anytime you want to protect things differently, okay, you want to have different characteristics of the transmitted channel, you need to have different transport channels. So in summary, transport channel tells us how we are sending information, how we are protecting the information. And one dedicated channel, convolutional coding, another dedicated channel, turbo coding, those are 2 simple examples. What is a physical channel? Basically here we are identifying who should be getting the data, who should be getting the voice. So for example, in case of LTE system, whatever resource blocks we have allocated to the user, right? Those resource blocks would constitute a physical channel for that UE. Normally, if you have a logical channel, that will be mapped onto some transport channel, and that transport channel will be mapped onto a physical channel. So for example, I will have some email, let's say. It's a type of information. I have some logical channel, dedicated traffic channel 1. I will protect that using turbo coding. I will specify the turbo coding by using a transport channel called dedicated channel. That will be my transport channel because I am doing turbo coding. And then I will map that onto a physical channel. In LTE, we have this physical downlink shared channel. Physical downlink shared channel, we will cover that later, but basically that carries our information for a specific user. Okay. So the user will get the information from that physical channel. So in summary, logical channel tells us what we are sending. Transport channel tells us how we are sending that information, how we are protecting. And physical channel tells us who should be getting that specific information. Okay, now you may be wondering where the channels are. We have protocol stack between E node B and the UE. So we have E node B and the UE. And the air interface is your UU air interface. over that air interface, this is the protocol stack that we have. We have physical layer, we have MAC layer, RLC, TCP, and RRC. Okay. And we have logical channel here. So RLC constructs logical channels. Then MAC layer will map the logical channel onto some transport channel. The physical channel will map a transport channel onto a specific physical channel. So that's where the channels exist. Okay? So, the next couple of slides are giving you the mappings among logical, transport, and physical channels. So, for example, in the downlinks, dedicated traffic channel would carry email, web page bits, voice or IP bits, etc. What is that we are sending? Type of information. That's why it is logical. Then we map that onto a transport channel called downlink shared channel. So in LTE, the name of our transport channel here, downlink shared channel. In basic UMTS, it's called DCH, dedicated. But for LTE, we call it downlink shared channel. Then this downlink shared channel will be mapped onto a physical channel called physical downlink shared channel. So from the user's perspective, it will retrieve the information from the physical downlink shared channel. That's what goes over the air. So over there, what are we sending? The physical channel, physical downlink shared channel. So we have those two tables so that you have the mapping between logical and transport, transport and physical. The standard has distinction between a channel and a signal. Physical signal. Signal means there is no upper layer information. No upper layer information. So for example, reference signal. Right? So we are sending predefined set of bits on the pilot for reference signal. So there is no information coming from the upper layer, no information coming from RRC, PDCP, RLC or MAC layers. No such information is sent by pilot. So that's why we say that, oh, the reference signal is an example of a physical signal. In contrast, the physical channel that carries the upper layer information. So for example, when we want to send email, that would be dedicated traffic channel generated by RLC layer. Then MAC layer will map that onto transport channel, which is your downlink shared channel. And we will protect it in certain way. For example, turbo coding, one way to protect information. And then physical layer will give you the physical channel by mapping the transport onto a physical, which is physical downlink shared channel in LTE. Don't worry about the acronyms. You have the PDF file, so you can look up whenever you wish. So that is the difference between the physical channel and physical signal. Okay, just a simple test for your short-term memory, whether you remember the main concepts regarding those three types of channels. I will give you a couple of minutes to work on this. Okay, so let's say 3 minutes, about 3 minutes for this question. So please think and then click. No need to rush. If you need more time, we will give you more time. Okay. Now, here we are looking for a true option. Only one statement is correct. Out of these four, only one is the correct statement. And please choose the correct statement. And just so that you know, logical channel tells us what we are sending, transport, how we are sending, and how we are protecting. Are we using convolution coding to protect? Are we using turbo coding to protect? Physical channel is telling us who should get the information. And feel free to look at your PDF file. Okay, this is not a closed book exam. Open book, open Google, any kind of thing. But you have only 3 minutes. About 2 minutes to go. And we have some questions. Oh, but we'll answer offline. And please participate in the poll. And in case you think that you have made a wrong selection, you can change your selection anytime. So it's dynamic. Okay. If you pick number 1, then you change your mind. You should have picked number 2, pick number 2 or 3, etc. So you can always do that. One minute to go. Okay, let's see what we have. Okay, so we improved our score little bit. So from 66% last time, now we are 72%. So at least we are moving in the right direction. So that is the correct answer. 2 transport channels. So in general, anytime you want to protect things differently, different amount of protection, then you need a different transport channels. So convolution coding, that is one way of protecting information. So we should use that for logical channel A. Another logical channel is turbo coding, another way of protecting information. So we need another transport channel. So 2 different transport channels should be used. Okay. Okay. So that's the generic concept that we have in terms of logical, transport, and physical channel. Okay, let's see. Perfect time for a short break. So we will have a 10-minute break, and once we come back from the break, we will unmute the bridge, and hoping that there is no noise interference problem, and then you should be able to ask questions using the audio bridge. So let's resume in about 10 minutes from now. And in the meantime, think about the questions